The million-fold power gap. FinalSpark's biological processors are currently operating at a power budget 1 million times lower than a standard H100 cluster for equivalent spike-based operations. While a traditional silicon chip requires hundreds of watts to simulate neural activity, these 16 brain organoids running in the Swiss lab consume almost zero energy to maintain their synaptic state. This is not a simulation of a neural network. It is a literal network of human neurons connected to a digital interface through multi-electrode arrays. The efficiency gap is so wide because biological systems do not require constant power to keep a gate open, using chemical gradients to store state instead. However, the current hardware overhead for life support systems complicates the raw math of these efficiency gains. The data throughput bottleneck. Accessing the neuroplatform 24/7 reveals a massive mechanical hurdle in the input-output layer. While silicon can move terabytes per second, FinalSpark's current multi-electrode arrays are limited to approximately 30 kilobits per second across the entire organoid. You are essentially trying to teach a high-dimensional system through a pinhole. Researchers are using dopamine and electrical pulses to trigger neuroplasticity, but the training latency is measured in hours rather than milliseconds. This slow feedback loop makes traditional backpropagation impossible, forcing devs to rely on reinforcement learning via chemical rewards. This biological clock speed is the primary reason Wetware is failing to compete with silicon on raw processing velocity. The 100-day deadline. Biological hardware has a built-in expiration date that no software patch can fix. FinalSpark organoids currently have a stable operational lifespan of approximately 100 days before cellular apoptosis degrades the signal quality. Think of it as a processor that literally rots as you use it. For developers, this means model weights cannot be permanently etched into a single physical unit. They must be transferred or replicated across new organoids in a process that is still highly experimental. This instability creates a massive reliability gap compared to silicon, which can run for a decade without physical degradation. This inherent fragility makes Wetware a poor candidate for mission-critical infrastructure, yet its metabolic efficiency keeps the research active. The signal under the noise. The move toward 24/7 Wetware access proves that biological computing is not a replacement for silicon logic, but a specialized tool for high-density adaptive sensing. By examining the throughput limits in the second section and the lifespan constraints in the third, it becomes clear that the value is in the biological ability to find patterns in noisy, low-power environments where silicon would burn through batteries. The real shift for builders is moving away from the idea of a bio-GPU toward a biosensor that learns. We are seeing the emergence of a hybrid architecture where silicon handles the high-speed logic and Wetware handles the extreme efficiency pattern matching. Watch for the first peer-reviewed papers on cross-organoid weight transfer in late 2026 as the true indicator of whether this hardware can scale beyond a lab curiosity. Subscribe for more.